Hello, and thank you for joining me today. Our topic today is Reaxys, retrieving relevant results. The concept of relevance in a chemical database is an interesting one because relevance is really in the eye of the beholder. If you want to be comprehensive, then everything is relevant. For example, if you need all articles published by a particular author. But if you are looking for precision, then even the largest database won't help you unless you have the right tools to get to that data. An example could be searching for a list of substances isolated from natural products containing 8-membered rings that have known anti-inflammatory activity. The concept of relevance is not new to Reaxys. Improvements to the database over the years have enabled users to find information in unique ways, with the foundation being relevant sources of information, which have recently increased and are now well over 16,000 periodicals. Relevance is seen in, for example, Reaxys ranking, which is used when presenting reaction results. This is based on an algorithm that takes into account the yield, number of steps, and other reaction details and assigns a weight. Those with fewer steps and fewer reactants are weighted more heavily, and those with low yields are weighted lower than those with higher yields. Reaxys medicinal chemistry is an excellent example of how a vast assortment of data can be turned into something that yields relevant results. In Reaxys medicinal chemistry, we've extracted data on bioactivity, targets, bioassays, cells, parameters, and we've organized and normalized it using px values to quantify the affinity of a compound. Data transparency is yet another way that Reaxys strives to bring you the most relevant results. There is an obvious advantage to seeing relevant terms in a database while you are typing. All data fields have an index that lets you see if your query is in there before you hit the search button. You can see different spellings, hyphens, and so forth, even misspellings that appeared in the original document. It also enables you to choose terms that may not have occurred to you. Let's take a look at some examples. Find out about the relationship between the refractive index and density of inorganic substances. The quickest and easiest way to find this information is to use Ask Reaxys. Type in the query and retrieve a list of citations. But another way would be to use the relevant data in Reaxys to come to a conclusion about the relationship between these two properties. I will select the Advanced Query theme. This allows you to access the entire data structure of not only Reaxys, but also of PubChem and eMolecules. Here you can string together complex queries using any of the fields and various data operators. Look for the refractive index fields, like wavelength and temperature. Here's 589 for the wavelength. Use proximity to show that the fields are related to each other. And then use the element symbol field with the not data operator and C to ensure that only inorganic compounds are retrieved. The results show inorganic substances with refractive index data taken at a wavelength of 589 and a temperature of 18 to 25 degrees. The density temperature should also be 18 to 25 degrees for the comparison, so refine the list. And here are the final results. The results can be exported to Excel, where the columns can be sorted, and this data seems to imply that the refractive index increases with increased density. The next example is the synthesis of pyrazoles. To do a literature search on this subject, use the literature theme and the citation basic index field. This field searches over titles, abstracts, authors, and keywords, and retrieves several thousand citations, like those shown here. or you can directly retrieve a list of relevant reactions by using Ask Reaxys. What if the results are not exactly what you had in mind? If you were really looking for cyclization type reactions, then the first few reactions are probably irrelevant. You can filter by reaction type, but filtering by substructure will result in more hits. This way you can eliminate all reactions where the reactants contain a parazole substructure or a dihydroparazole substructure. And to ensure that I cover all possibilities regarding single and double bonds, I'll open the structure editor, use the Any Bond feature, return and select reactant, substructure on all, and exclude. Here's over 300,000 reactions that can be further filtered by many other criteria. I happen to find the history of parazole synthesis in Wikipedia, where it mentions German chemist Hans von Pechmann. Is he one of the authors in our list? The list is too long to generate, but you can filter by value and type in Pechmann with wildcards at the beginning and the end. Here's one. And here's all the reactions from that paper. Here's another reaction search. Reduction of a nitrile to an amine in the presence of a non-reacting nitro group. The reaction shown here will retrieve hits with the nitro and the amine on the same ring, as well as hits with the nitro and the amine on different rings. What if you want to limit results to only those with the nitro and amine on different rings? Here are the steps for setting up the whole query. First, draw the aromatic nitrile and aromatic amine. And then type NO2 and click to add this fragment. Add a bond and add the CYC abbreviation. Add the arrow. Merge the reactant fragments to ensure that they appear in the same molecule. Click the Chemistry menu and select Chemistry, Merge Reactants. Then do the same for the products. Map the reaction. To prevent substituents on the N, click the Select tool, click the N, and type period S asterisk, one after the other. Notice that the nitro and the amino are on different rings in the results. Thank you for watching. If you have any questions, please contact me directly at c.fleming@elsevier.com. Thank you.